Did you score, Trayden? Oh, bummer. It's always next weekend. Okay, we have a homework out there, right? It's due Wednesday. I think that was the right thing to say this time. Okay. It's due Wednesday. We have a quiz over that material. It's going to be available on Thursday through the end of Sunday. Okay. Take your time, right? You have 2 hours to do this. Right? I know it's kind of hard, depending on when you decide to do it, if it's a weekend, to take out 2 hours of your weekend. But I think talking to some of you, it seems like, I think haste is maybe making those quiz scores a little bit lower than they could be. There's a lot of resources there for you when you're taking the quiz, right? You can actually go to the text section and read that and review some of that material while you're taking the...
So that doesn't affect your quiz score?
No. Yeah, that's free info. Check out the text, okay? You have 2 hours to check out the text and do the exam. But I'd say most most of the quizzes, I can look and see how long each of you spent going through the quiz, okay? And hardly anybody makes it past an hour, okay? So, anyway, I know it's hard. It might be the weekend. That's why I give you the option to start it on Thursday if you want to, right?
What's the quickest time you've seen?
Quickest time? I don't know. Probably, like, I feel like there were some below 10 minutes.
I think I've done one in about 5.
Yeah. So, I don't know what I can't remember the grades that were reflected based on that time, but it could go either way. Maybe you're a really good guesser, right? They're all, well, I guess some of them are not multiple choice, so. Okay, so to pick up where we left off on Friday, right, we had this motor. It applied 25 horsepower to this shaft system that drives 2 gears. Each of those gears are taking power off of the shaft system, right? They said the first gear takes 60%, or gear C took 60% of the power, or 15 horsepower, and then the last gear takes off the remaining 10 horsepower. And they asked us, what is the slowest permissible rotation speed for the motor? So we went through, given our two expressions, right, relating torque. We have our torque to stress relationship, T equals tau max times J over C. And then we have power equals torque times rotational speed, right, omega. And so based on rearranging omega, we can get this equation as in power divided by the maximum torque equals the rotational speed. Well, if that torque is limited, like in our case, right, our shear stress, our allowable shear stress for the steel tubes, we were told is 8,000 psi. So they're limiting how much torque we can apply to the system. Well, if they're limiting the amount of torque we apply to the system, and we're given the amount of power that's supplied, right, we're essentially given a requirement as to the rotational speed. Right? What's the slowest permissible? So in order to do that, we need to calculate the maximum torque first, which is our maximum shear stress times the polar moment of inertia divided by the max radius. We calculated max radius and our polar moment of inertia. Now we can go through and calculate what our maximum shear stress or maximum torque is. 8,000 pounds per square inch, right? Times J, which is 0.34 inches to the fourth, all over the radius, 0.075, or 0.75, sorry. Our units work out to be 3624 pound inches. I want to make it to feet, so I divide by 12, right? Inches per foot. So we get this max torque equal to 302 pound-feet. Right? Our moment, our max moment, or our max torque is 302 foot-pounds. Well, now that we have our maximum torque, we know how much power we need to deliver, we can now calculate our omega equals power over max torque. Power, we're given in horsepower. We know there's 550 foot-pounds per second per 1 horsepower. We're going to divide all this by the maximum torque. And we get our answer in radians per second, right? Powers cancel, foot-pounds cancel. We get essentially 1 over seconds. Unitless over seconds or radians per second. They wanted to know our revolutions per minute, right? What is the slowest permissible rotational speed for the motor? Well, this is the slowest rotational speed for the shaft, right? Because that's what's dealing with torque. And so we've got omega equals 45.5 radians per second. 1 revolution we know is 2 pi radians. We have 60 seconds per minute, and we get our typical rotational speed units of revolutions per minute, or RPM, 435 RPM. So if we want to ensure that we don't exceed the maximum shear stress of the shaft, and we provide enough horsepower, that being 25 horsepower into shaft 1, right? We've got to rotate this shaft here at 435 RPM in order to get that without exceeding the max torque. But we want to know, well, how fast does the motor have to spin, right? Because we have this gear ratio going on here. Well, the RPM of the motor equals the rotational speed of shaft 1 times our gear ratio, right? So in our case, with speed, the gear ratio flips. So now we're looking at 435 RPM times the diameter of the shaft's pulley divided by the diameter of the motor's pulley, or we get the RPM of the motor needs to be 1,522 RPM. Does that make sense? Right? A lot of moving pieces here. Anything less than that, and we're not going to provide the power required, right? Anything less than that, we're not going to provide the power required. Okay. Well, just like with axial systems, we have indeterminate systems with respect to torsion too. Right? Indeterminate, go through the process to devise a solution for indeterminate systems. But indeterminate just means that there are more unknowns than equations of equilibrium, right? Our equations of equilibrium do not allow us to calculate forces. Right? More unknowns. more unknowns than equations of equilibrium. Right? We have some of the moments and some of the forces. Well, if we're looking at true, pure torsion systems, ignoring some of the gravity respects, right? We really only have one equation of equilibrium, the sum of the moments along the axis of the shaft. Right? That's where all the forces are acting, is along the axis of the shaft. So if we have a system that has two unknowns in it, then we have an indeterminate system. Right? And we determine if it's indeterminate through our same process as we went through with axial forces, okay? We start with our free body diagram. This is where we assume coordinates and find expressions or expression where sum of the moments equals 0, right? Or sum of the torques, essentially. Torque is a moment. So in this case, we're assuming a coordinate system, right? Along the axis of the shaft, one direction or the other. And then we just sum moments about that axis, right? And that has to equal 0. If we have one unknown and we sum moments, right, we're going to be able to solve for our unknown, and this would be a determinate system. If we have more than one unknown, then we're going to need to continue down this process path, right, where we develop additional equations that relate forces and deformations so that we can then have an additional equation and solve for our forces. So if we do have an indeterminate system, we need to now assess or determine how a system will deform. Right, with axial systems, we had one of the relationships was, and you had a homework on it where we had the rigid steel bar or rigid bar, right, and it was connected with a bunch of different axial members. And if the bar rotated, right, we could come up with a relationship between the deformation in one rod versus deformation in another. Another one is if we had those rods in series, right, and they were between two fixed plates, we could say that the deformation of all the rods has to equal 0 because it's between a fixed set distance, right? The other one is if we had two materials that were, say, glued together, but they both extended between two plates. So if one material extends, the other one's got to extend, right, because they're connected together. So very similarly to that, see how well I can draw here. Right, if we had a shaft that cantilevered stuck out of this wall, okay, and that shaft was made out, it was like a donut where it had an outside pipe and inside that pipe was a different material, right, and they were connected throughout their length. And we applied a torque at the end of that cantilevered rod that came off the wall here, okay, we could then come up with a relationship for its deformation, right? We could say that if this was, oops, inside was material 1 and outside was material 2. We could say that deformation of all members are equal. Right? That just says that the twist of the inner rod has to equal the twist of the outer rod, right? They're connected throughout. It's essentially the torsional case for the axial case that we looked at before for indeterminate systems. We can have another one. similar with the axial indeterminate systems. With torsional indeterminate systems, you might have two different rods or shafts, right? Different materials that are between two fixed ends, okay? You apply a torque in the middle. Our total deformation in this case, right? Total deformation equals zero, right? Deformation. If the supports can't rotate, we apply torque at the center here. Right? These shafts are going to rotate the same, but in opposite directions. So the total deformation or the total twist of that system has to equal zero. Right? Well, we also have gears or pulleys in torsional systems, right? So we can come up with angular relationships of deformation right, so A rotates proportionally to B. Via gear ratios, right? We had a torque applied, right, at A. We had a torque applied at A. We knew some of the geometric properties of this shaft, right? We'd essentially be able to calculate what the rotation is going to be at A, the gear A, right? And if we rotate this shaft at A, we know that it's going to be proportional to rotating a certain amount of rotation at B based on the changes in those gear ratios. So we take these relationships. Bless you. Right? You take these relationships, and now we can relate force and deformation. Right? This is essentially our torque twist relationship. Very similar to what we did in axial members, right? FL over AE. We're relating force and deformation. Well, we have an equation that relates twist with applied torque, right? TL over JG. So now we can take this force deformation relationship, plug it into the deformation relationship that we determined from the overall system. Right? That would be step 4. So we get to combine steps 2 and 3 so that the geometry of deformation is expressed using forces. This is called compatibility. saying the geometry of deformation is expressed using forces. So you're finding a relationship that relates how the system's going to deform, and you know what those deformations are in terms of applied forces, right? Internal forces. So when you substitute those together, you essentially get this relationship that you know the geometry of deformation based on the applied forces. And this gives you another equation that you can use with your equation of equilibrium. So now we get to solve using equations, or our equilibrium equation, right? Right, this is where we get to solve for the torque, right? The internal forces, that's really what we're trying to determine out of here. Some of the moments we're going to be summing our torques. We're going to have more torques that we don't know than we do know. This additional equation here, which is going to be an equation that relates deformation with respect to applied torques, is going to give us the ability to solve for a torque in terms of another. Take that, plug it into our moment equation. We can solve for all of our internal forces, or our torques. Finally, from there, we can use our equation for internal, our maximum shear stress is based on our polar moment of inertia, our maximum radius of our shaft, as well as the applied torque.
Quick question.
Yes.
So we use C to denote the maximum radius. Is that for if we have, say, a tapered shaft? Is that why we do that? Or why isn't it just R radius?
So C is just denoting the max radius. It's just the way that the nomenclature works. I mean, that's a very good point. I don't know why they wouldn't just use R. Yes?
Was it, you used rho to determine further?
Yes, distance out. But then when rho equals R, that is C. Makes sense, right? God. Yeah, love it. Okay, obviously we're going to go through an example. The last torsional, well, that's not true. We're going to go through stress concentrations, but we have an example. We have two pipes. They're rigidly connected at both ends. What's that saying? Well, that says that there's no rotation, right, at A and C, or at the extremes of our two pipes. They say pipe 1 is made out of aluminum and pipe 2 is made out of steel. They give us our shear modulus for each of those, which is good to know. They give us the dimensions of each of our pipes. So our aluminum pipe is 140 millimeters in diameter, maximum diameter, and it has a thickness of 7 millimeters. Steel pipe is 6 millimeters thick. And the maximum radius is 100 millimeters. Okay. They say that we have a concentrated torque, TB, applied at the flange, or the connection between the two steel pipes, of 15 kilonewton meters. Okay. And they ask us for a couple things. One, they said, what's the maximum shear stress in each of the two pipes? And what is the rotation angle of flange B relative to support A? So essentially, how far did this flange rotate with respect to the ends? Well, if we just follow what I just went through, right? The solution would be 1, starting with a free body diagram. Well, if I decide to draw a free body diagram, I'm going to cut out that middle section. I'm going to take the middle section out. We really want to know internal torques. right? Internal torque's going to allow us to calculate our maximum shear stress. Internal torques are also going to allow us to calculate our deformation or our twist, how far each of those shafts are going to twist. So I really want to know what the shear or the torque is inside each of those pipes. So if I draw a free body diagram that depicts each of those torques, say we had our flange connection. Make this a little truer to, and we have our aluminum pipe off to the left, which is a little bit larger in diameter than our steel pipe. We need to assume coordinates. I'm going to assume we have a positive x to the right, okay? Well, if we look at our applied torque and we use the right-hand rule, right, our applied torque at B, shown as a double vector arrow, right, would be facing off to the right. Right-hand rule, facing off to the right. Then we're going to have internal torques in rod 1 and rod 2. Those internal torques, I can assume at this point any direction I want, right? The math should show me which direction they act. Well, I'm going to assume T1 acts to the left. Don't know which direction this really acts, but I'm going to assume it acts to the left. And I'm going to assume T2, or the torque in shaft 2, acts to the right. Okay? Well, if we sum moments about the x-axis, right? That's essentially the only equilibrium equation we have. Some moments about the x, we have torque B, right? It's acting in the positive x direction. Double-headed vector arrow is going to the right in the positive direction for our x-axis we assumed. We also have torque 2. I assumed acts in that direction. So I'm going to add torque 2. And I'm finally going to take off torque 1, right? Minus T1. Even though if we look at the sign convention for torque, positive outward, normal is positive. So when we go to calculate, say, deformation or the maximum shear stresses, things like that, this torque is positive, right? Same with this torque is positive. But if we're summing moments, right, and we assume a coordinate direction, this being positive x to the right, we follow that sign convention in a free body diagram. Okay, so we have 0 equals torque B, that's in the positive direction. Torque 2, I guessed it was going to act to the right. And torque 1 is acting to the left, right? I guessed that. Well, we have one additional unknown that we have equations for. We have some of the moments in the x direction. We have one known value, that's the torque at B they gave us. We don't know what the torque is in each of the shafts, so we have one, right, this is a indeterminate to the first degree. We have one additional unknown that we have equations for. So being that it is indeterminate, we need to assess the deformation. That is step 2. So if we work through assessing our deformation, well, out of the 3 different relationships that I presented, we have the proportional, which is gear ratio driven, no gears or pulleys in this. We've got the parallel systems or systems in series. Parallel systems means a shaft within a shaft. Okay, don't have that. So we have this system in series, right, where we have fixed supports on both ends. We have fixed supports at both ends that are not going to allow these shafts to rotate at the ends. That means the shaft rotation of 1 has to equal the shaft rotation of 2, or the total 0 equals the twist at 1 plus the twist at 2. Okay. Now we need to relate torque to twist. We do that through our torque-twist relationship. So we have T1, L1, J1, G1 is the rotation at 1, right? Deformation. Deformation of 2 is the torque at 2, the length of 2, polar moment of inertia of 2, and the modulus of, or the shear modulus of 2. Okay. Well, we have everything we need to calculate 3 of those items in each of those, right? We've got the lengths, we've got the polar moment of inertias we can calculate, and they gave us the shear modulus. So if we start by calculating our polar moments of inertia, pi over 32, right? Outside to the 4th minus inside to the 4th. I'm not going to bore you with all of that. This gets incredibly tedious. So essentially 140 millimeters minus 126 millimeters to the 4th times pi over 32, and you get that. Polar moment inertia of 2. Same thing, it's a pipe. It could be a solid steel shaft, okay? All that would change is our polar moment inertia, right? In this case, because it's a smaller diameter, it has a smaller resistance to twist, smaller stiffness to twist. So now that we have this torque-twist relationship, yes, Brendan?
Oh, and just to clarify, inside diameter is 2 times the thickness, right?
Inside diameter, it would be the outside diameter minus 2 times the thickness, yes. So now that we have this relationship for torque and twist, okay, we have all of the information in here except for these torques. We can take this torque-twist relationship, plug it into the deformation relationship we established, and now we're going to get an equation very similar to this, right? Where we have torque 2 and torque 1 that are going to be in a single expression. So if we start by, so we get a little cross-eyed here, 4. So we want to combine 2 and 3. Well, if we do that, we're essentially saying that the twist at 1 plus the twist at 2 equals 0, or T1, L1, J1, G1 plus T2, L2, J2, G2 equals 0. Well, we can rearrange that equation to give us something in terms of one of the torques, right? 2 equations, 2 unknowns. We're going to solve one equation for the other unknown, take that and plug back into the original equation. So I chose to rearrange this for torque 1. You could as easily have rearranged it for torque 2. So I said torque 1 is negative torque 2, L2, L1, J1, J2, G1, G2. All right, that's our expression. We have everything to the right of torque 2. We have our length of our shafts, we have polar moment of inertia for each of the shafts, we have the shear modulus for the shafts. I'm not going to bore you with all of that, but you essentially just need to input all of those values, and when you do that, you land with an expression that says T1 is minus 0.894 T2. So using our relationship for deformation, saying that the deformation has to equal 0 as we move from one side to the other because these ends are fixed. That means the shaft deformation, or the deformation of shaft 1 plus deformation of shaft 2 has to equal 0. doing that, plugging in our torque twist relationship, we essentially establish this expression. That's the relationship of torque 1 with respect to the relationship, or with respect to torque 2. Now, we can go back to our equilibrium equation. We have an expression of T1 in terms of T2. We can replace T1. So we get some of the moments about the x-axis we know is 0. We decided that it was the torque at B plus the torque at 2 minus the torque at 1. Or we can rearrange this and say that torque at B equals the torque at 1 minus the torque at 2. We know the torque at B they gave us was 15 kilonewton meters, right? 15 kilonewton meters. And we also know that torque 1, well, that's negative 0.894 torque 2. I'm going to place that in there. I'm going to rearrange this. I'm going to say 15 kilonewton meters equals negative 0.894 torque 2 minus torque 2. What's that mean? Well, we have negative 1.894 torque 2 equals our 15 kilonewton meters. Well, if we divide 15 kilonewton meters by negative 1.894, we would get that the torque in shaft 2 equals negative 7.92 kilonewton meters. And if we plug back into our equation up above, saying that T1 is negative 0.894 T2, we get 7.063 kilonewton meters. Yes, Brendan.
So do these still have compression and tension? Like the sign, so we have a negative torque,
Yeah.
but that doesn't mean compression, right?
Yeah, so I was just about to mention the fact that when we did our equilibrium equation, we assumed a sign convention that said that T1 was negative because it acted to the left and T2 was positive because it acted to the right. Well, now we've just established what direction each of those go by by our outputs here. So it says T2 is negative 7.92 kilonewtons, or kilonewton meters. So what does that mean? Well, T2 actually acts in the other direction, which makes sense. If you looked at this and you applied a torque in one direction, both the steel pipes are going to resist that, right? The steel and the aluminum pipe are going to resist that. I did this to show you that the output that you get is going to establish the direction of these internal torques, okay? With respect to the assumed sign convention that you started with when you developed your free body diagram, okay? Which makes sense in our case because it's saying that T2 is actually acting in the opposite direction. Does that help you out, Brendan?
Mm-hmm.
Yes.
So in this case, because T2 acts in the opposite direction that we drew it, it is actually a negative torque because it's into, it would be, the arrow should be pointing into the...
Correct. Correct. Yeah, so essentially because outward normal is positive, right, the sign convention for torque, so these two are essentially positive torques, but because we just calculated that T2 acts in the opposite direction, this torque is technically negative, right? It is going to rotate the shaft in a negative direction because it is a negative torque. It's kind of confusing, trying to separate the free body diagram from the actual torque, okay? So now that we've established the magnitudes of our torque and the actual directions that they act, we can solve for part A. Right, which was asking us what is the maximum shear stress in each of these two pipes. Well, we know that the maximum shear stress is based on the applied torque, our max radius, they love to call it C, okay, for some reason. And so that's a function of the geometric properties of the shaft and the applied torque in the shaft. In our case, we've got one equals T1 C1 over J1. I'm not going to bore you with the rest of this, but I get 38.2 newtons per millimeter squared. Right, this is a megapascal. Remember to keep your units consistent. If our torques came in kilonewton meters, we would need to convert it to Newton millimeters. Right? Max radius we should have in millimeters, and then J's already in millimeters.
So for your radius there, did you use that with reference to the outside diameter of the pipe?
Yes.
Okay.
Yes. Right, our shear stresses vary linearly from 0 at the center out to a maximum at the outside radius of the pipe. If we do that same same expression for torque 2, we get 100.8 megapascals. J becomes a big driver in this. Right? If we look at the two polar moments of inertia of our two pipes, well, the aluminum pipe one is about 4 times as much, right? 3.5 times as much as our steel pipe. So that denominator drives that stress way up in the steel pipe because it's not as stiff. Because it's not as stiff, our stresses go up. Now if we go through and we solve part B, right? They asked us how much, with this applied torque, how much did this flange rotate with respect to plate A? Right, we have this torque twist relationship now. We have torque 1, and we have all the other geometric parameters. We get 0.189 radians, okay? This would be 7063 Newton meters times 1,000 millimeters per meter times 9,000 millimeters, because it was 9 meters long. Then we have 12 times 12.97 times 10 to the 6th millimeters to the 4th. That was our polar moment of inertia of the shaft 1, and it was 26 gigapascals. Which is 26,000 megapascals, which is 26,000 newtons per millimeter squared. Okay. That way all of these units cancel and we end up with just with radians, okay, unitless. This is a positive radians, right? 0.189 because our torque is positive, because it's outward normal. T1, outward from the face. So it has a positive rotation. If we were to calculate the deflection of the shaft 2 at this point, we're gonna come up with the exact same answer, but it's gonna be negative, right? So if we went through and put in, we get T2, L2, J2, G2. We're gonna get negative 0.189 radians. Which if we went back to our original deformation relationship, right? That relationship holds true. Right? Because the torque is now negative, because it's acting towards the face. Rotation is negative. So when we add the rotation of 1 plus the rotation of 2, we get 0. Which this should check out because this is one of the bases we used to calculate the torques in the first place, right? It's one of it's the relationship we used. Any questions? What's that? Kind of needy, aren't you? Units. Rotations in radians is unitless. All of these should cancel out. Up above, you should land with some sort of stress. Stress would be megapascals or pascals, right? Newtons per millimeter squared or megapascal. So you want to make sure your torque is in Newton millimeters, your max radius is in millimeters, and your polar moment of inertia is in millimeters. All right, we're going to step away from this torque, at least, and get back to axial, which torque and axial loads, right, are similar. They're acting along the axis of a long, slender member. We're going to talk about stress concentrations. I already started talking about these earlier in axial, but I wanted to wait until we got torsion done. So in the book, this is chapters 5 and 6 in those sections, right? Axial is chapter 5. We have this principle. It's called St. Venant's principle. We talked about it briefly during axial loads. And really the basis was, right, after we discussed, we had a concentrated load on a long, slender member, okay? We're going to have some localized stresses that happened at the applied force, right? Makes sense, okay? If you were to put like this piece of rebar, okay? And you put a nail on the top of it, okay, and you put 10,000 pounds on that nail, right at the surface where the nail is driven, right, you're going to have a lot of stresses right around the nail head, okay, right, or nail tip. And then as we work our way down into this piece of rebar, right, those stresses will slowly dissipate, or not dissipate, but spread out, okay? And St. Venant's principle says that once you get to essentially the depth of the width of that cross-section, essentially, once you get into your cross-section, the same distance as the width of the cross-section, you've essentially established a uniform stress, right? That's where we can use our uniform tensile stress. It's force over the area, and the area we use is the total area of the cross-section. So as you imagine for this rebar, if you put something in the center of it, it doesn't take very long until you're looking at a uniform stress across the entire piece of rebar, right? Well, that's where we have applied forces. Well, if we had, say, a piece of steel plate, see what we can find over here, okay? Say this is steel and not plastic, okay? And we decided to drill a bunch of holes in it. We might decide to put some notches in it in order to make it fit in the situation or conditions that we have for it, okay? Those stresses, as they travel through, so now we're not looking really at the ends of the member, but something happening through the length of the member, okay, our stress has to essentially travel through that discontinuity. Okay? It's got to go around the hole, around the notch, or through some sort of pinch. And so we get concentrations at interruptions. In our stress path. So you can imagine each one of these lines is what they call a stress trajectory. Okay? And those stresses are parallel to our normal stresses. And so we'll talk about it on Wednesday on how the moving of these stresses, right? Compressing them, driving them around the discontinuity increases our stresses in our member. Sweet.